All right, good afternoon, good evening, ladies and gentlemen. We are going to be looking at our final section of Chapter 4, Section 4.6, dealing with what we call related rates. This is going to be another one of those tough sections like 4.4, and my only thought here is that when these type of problems get tough, it means it's a much better problem. All right, so you know my understanding of good problems usually mean hard problems. But I also mean these are really good problems because they're actually real life problems. Something that you could use calculus for in every day. All right, so let's look at what this is going to look like. Here's an example. Suppose you have something moving along some curve on a plane like x and y axes, and it has a coordinate x of y. They're differentiable functions with time t. If d is the distance from the origin, well, there's something you actually know, then using the chain rule, we can find an equation that relates the derivative of distance. So notice this is dd dt, the derivative of distance with respect to time. We can look at the derivative of x with respect to time and the derivative of y with respect to time. So what you're going to see here in a little bit is this is going to be a lot of implicit differentiation and substitution, equations that you're familiar with, equations you might not remember off the top of your head. But first one being distance formula. All right, so if you have some point that's on this xy axis and it's xy, and we're talking about the distance from the origin, there are some things we know. We know that distance is equal to the square root of the x coordinate plus the y coordinate. Really simple math that you already know how to do. Now, the thing that we're going to be doing here, though, is because it's changing over time, we're going to be finding rates. That's what all these are. This is the rate of distance with respect to time. This is the rate of the x and the rate of the y value. Now, this particular problem really has no meaning other than what we're going to be doing. All right, so what we're going to be doing in this particular equation, notice we're taking the derivative with respect to t, but there are no t's. So what we're going to be doing is a lot of implicit differentiation. All right, so if we take the derivative of big D with respect to t, we just get derivative of d with respect to t. And then notice I made mention of, or the textbook made mention of, the chain rule here. So there's a lot of chain rule stuff going on in this. We have to take the derivative of the square root function. So we're going to get 1 over 2 times the radical x squared plus y squared. But we have to do the chain rule also. And the chain rule tells us take the derivative of the inside piece as well. And the derivative of the inside piece is the derivative of x squared, which is 2x. But here's the thing, we're not taking the derivative with respect to x, we're taking it with respect to t, so implicitly says I need a dx dt, and when I take the derivative of y, I also have to do the same thing of dy dt. It's kind of like what we did with implicit and where we had like a y prime. And the only reason we didn't do it with x was because we were taking the derivative with respect to x. But now everything we're doing is with respect to time. All right, so notice what the question was. We found an equation that relates the derivative of distance with respect to time, and it relates it to the derivative of x with respect to time and the derivative of y with respect to time. Now some of you are going, what does this have to do with anything? It doesn't. But it shows us kind of the process that we're going to be doing throughout this lesson. All right, so I have 3 examples. I'm taking them straight from the textbook because they're good examples, and it's another one of those sections where I could sit here and do hours and hours of examples, and you'll still not see one that you're going to come across a problem that I didn't do an example for. All right, so I mentioned something later I'm going to talk about as we get to the end of this. So first example. Oh, sorry. Got to stop at the examples. Got to start with the strategies. All right, so strategies being almost exactly like we did for section 4.4. They're just strategies. So first thing is you need to understand the problem. So you need to figure out what variable or what rate that you are seeking. So do you need to know the derivative with, do you need to find the rate of the x value? Do you need to find the rate of change for height or volume? What do you need to find? And then you also need to identify what rates you know. So you notice in this last piece here, there's 1, 2, 3 different rates going on. You're going to need to know some of them so you can solve for the third one, for the last one. All right, so identify what you want, identify what you know. That's kind of basic things anyway. I mean, that's something you should know how to do anyway. All right, you need to develop a mathematical model of the problem. So usually means drawing a picture. Pictures are very, very helpful. Just like when we did our trigonometry, pictures are helpful. Just like we did 4.4, those pictures that were in the book were super helpful. Pictures you drew yourself were super, super helpful. Then you need to write an equation relating the variables that you seek with the variables that you know. And these are usually geometric equations. We're going to be dealing with volume. We're going to be dealing with right triangles. So you know right triangle trig. You know Pythagorean theorem. Those are kind of the hinting at what we're looking at for our examples on this presentation. Number 4, you're going to want to differentiate both sides just like we did with that first example there. And remember, you have to do it implicitly with respect to time. So all of your variables have to be differentiated with respect to time. Remember to follow all of your rules, all of your chain rules, all of your product rules, quotient rules, all that sort of fun stuff. And then you're going to substitute any values that you know after you've taken the derivative. And this is very important that you do this after, because if you put the numbers in before, you've now made a solid picture, not a changeable picture. Like if a car's driving away, but you told me it was exactly 8 miles away, and you used 8 in your equation, you've now made it so that 8 is a solid number, not a changeable number. It's really weird to think about, but you can't do any substitution till the end. So we start with variables, we differentiate, then we put in the things that we know. And after we do so, this same thing is 4.4. Very last thing you do is you interpret the solution and just make sure you understand what it means and make sure that it makes sense. That sort of idea. All right, so those are just basic guidelines. I kind of follow this along. I don't say, oh, now I'm doing number 1, now I'm doing number 2. They're just kind of helpful hints along the way. All right, so first problem. We have a hot air balloon. It's rising straight up from a level field, and somebody's tracking it. And when it gets to 500 feet from the liftoff point, horizontal distance, and at that moment, the rangefinder's elevation angle, or angle of elevation, if you remember that from trigonometry, is pi fourths, or 45 degrees. We're just going to leave it in radians because we usually do for calculus. And the angle is increasing at the rate of 0.14 radians per minute. And how fast is the balloon rising at that moment? So here's some things we know. Let's just think about what we seek and what we know. We seek how fast is the balloon rising? So we're going to call it h because the balloon's height, right? So we want to know what is dh dt. What is the rate of the height? How fast is that increasing? And we know another rate because it tells you. It tells you the angle is increasing at the rate of 0.14 radians. So angles, we like to use the letter theta. So the derivative of theta with respect to time is 0.14. So that's like that first step. I figured out what I want and I figure out what I know. All right, so let's go on to the blank page here and we're going to set this up. So you're on level ground and the balloon is at some sort of level up here. We have our balloon. It's kind of an ugly balloon because I'm not a very good drawer. Okay, and this is some height off the ground, and this is some 500 feet away. Right, we're dealing with feet, right? Feet, good. And there's somebody down here looking at the balloon with a rangefinder and says that his angle of elevation, which is this, is pi force. All right, so we need to compare theta to height. Well, it's pretty simple if you think about this as a right triangle, because it is a right triangle, because the height is a vertical distance. Which means I have side opposite and side adjacent. So I know that the tangent of theta is equal to height over 500. All right. So what we need to do now, I'm just going to rotate, because I want to figure out derivative of h with respect to t. I'm going to get h by itself and get a nice non-fraction thing going here. So 500 tangent theta. Now, notice I haven't used this pi fourths yet, because I don't want to yet. I did use the 500, but that's an okay one, because the 500 distance, that's not the changing piece. The angle is changing. All right, so now I need to find derivative. So the derivative of h with respect to t is, that's just a constant times tangent, the derivative of tangent being secant squared. Now here's where it gets very confusing for some of you. Theta is a changing value, which means it's actually one of my variables. So when I take the derivative, I took the derivative of tangent, but the chain rule says take the derivative of tangent multiplied by the derivative of the inside thing. Since theta is a variable, I also have to multiply by the derivative of theta with respect to t. Now, there's some things that we know that we can plug in. I'm looking for dh dt, so I don't know what this one is, but I do know what theta is, and I do know what d theta dt is. So I can say dh dt is 500 times the secant of pi fourths, that's the angle that we're given, squared, because that's what secant squared is, by the way. It's secant of pi fourths squared, times the change of the angle with respect to time, and we know that to be 0.14. And if we plug this into our calculator, secant of pi fourths is root 2, so if we square that, we get 2. So 500 times 2 times 0.14 is 140. But what is that? Well, that is dh dt. dh dt is 140. Now, here's where you have to pay attention. It's not just 140, it's 140 what? And it's a rate, so it's the change in height over time, which means it's feet per what? What units are we using here? I forget. Minute. So it's 140 feet per minute. That's how fast that balloon is rising. See how cool that is? Just if you're standing at the, what is that? Like 2.5 or 5 football, not 5 football fields, 1 2/3 of a football field, almost 2 football fields away, and you had a rangefinder and you could figure out your angle of elevation if you're looking up at the balloon, you could actually figure out how fast that balloon was rising. That's just, to me, that's awesome. And it's just using some simple calculus. All right, so that's the first one. Let's go to the second one. We have 3 of them today. All right, so the next one is a police cruiser problem. It's some long words. I mean, it's a lot of words, but who cares, right? You guys have to write 5-page essays every once in a while. All right, so you're approaching a right-angled intersection. That's good. We know some stuff about right triangles. You're approaching it from the north in a police cruiser. It's chasing a car, turns east. Okay, some stuff. When the cruiser is 0.6 of a mile north of the intersection and the car is 0.8 of a mile to the east, the policeman uses his radar, finds the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles an hour at the instant of the measurement, what is the speed of the car? All right, so if we think about this, I know the policeman is here. And he is moving, he's north of the intersection, so he's moving south. That's going to come in handy for us in a minute. And at some right-angled intersection, the bad guy is out here. Let's call him the speeder. All right, and he knows, I mean, obviously it's a right triangle. The policeman can see the speeder, and he knows that this distance is changing at 20 miles per hour. Now, if we just let these all be variables here, there are some things that we know and some things that we don't know. One thing that we want to know is how fast the car is moving. Well, that is this distance here, the rate of this change, which means we need to know dy dt. And we do know the other ones. We know that dx dt, let me write a good T. We know dx dt, and we know dz dt. Now, dz dt is the change of this hypotenuse length, which is how fast the speeder is getting away from or opening up the distance between them. And we know this to be 20. Now, here's where this gets a little confusing, partially. This distance x is actually decreasing because the policeman is getting closer to the intersection. So we're going to actually say that this is a negative 60. All right, so now we need dy dt. So notice I'm not using any angles here, but we're still using a right triangle, so there's some stuff I know. I know that x squared plus y squared equals z squared. I hope you all know that too. Very simple Pythagorean theorem. This is the equation that we're going to use. And we're going to take the derivative of this with respect to t. So I'm going to get 2x dx dt plus 2y dy dt equals 2z dz dt. Now you may be wondering, I was like, hey mister, you haven't used the distances yet. And you're right, because they're not needed until we've taken the derivative in this problem. All right, so now you'll notice we have length x. Well, we know the length of x. X is that distance between the policeman and the intersection. Well, the distance between the policeman and the intersection is what? What is it, actually? Intersection is 0.6 from the cruiser and 0.8 from the car. So we know that this y value is actually 0.8, and this x value is 0.6. And notice all this stuff that we have and all the stuff that we know. So 2 times x, which is 0.6, dx dt, which is negative 60, plus 2 times y. Technically, we could have gotten rid of all the 2's here, but I just forgot about it. Okay, and kind of left them. 0.8. Now, we don't know dy dt. Now, here also, we don't know what the distance z is. Or rather, we do. Z, we already know, is the square root of x squared plus y squared. And we're going to use that. And that's just another use of the Pythagorean theorem. We know that z distance is the square root of the leg squared, the sum of the legs squared. So we're going to use that knowledge. We're going to get square root of 0.6 squared plus 0.8 squared. And we know dz dt to be 20. Well, that's kind of nice because now that's everything I need to know. So what I'm going to do is I'm going to just kind of cancel out these 2's because I don't need them. I'm going to get this to be negative 3.6 plus 0.8 dy dt equals, well, if I do this on my calculator here, the square root of 0.6 squared plus 0.8 squared is, oh, Really? 1? That's just too easy. Man, makes our life easier here. So this is a 1 times 20, and I'm going to do a little arrow up here, and I'm going to say, okay, if I can add 3.6, I get 0.8 dy dt equals 20 plus 3.6, so 23.6. Oops, not 3.6. Man, I wish some of you were here with me when I make these stupid mistakes, because then I don't figure out them too late. All right, my error. I hope you caught that as well. 0.6 times negative 60 is not 3.6. It is 36. All right, so if I add 36 to both sides, I get 56. And if I divide both sides by 0.8, I get the change of y with respect to t to be 70, and we know we're working in miles per hour. So that means the policeman is a very slow driver compared to the speedster. The policeman is only driving 60 miles an hour, the speeder is driving 70, and he will never catch him at this rate. So he's not a very smart cop. All right, but that has nothing to do with the problem. All right, so notice we basically just went from the Pythagorean theorem straight down to a rate. It's kind of cool. All right, last problem for this particular lesson. This particular problem, every year when I wasn't teaching calculus, I always had somebody come and ask me how to do this problem. These conical tanks. Okay, this is not comical tanks, conical tanks. So it's a cone. So you have water running into a conical tank at a rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. And how fast is the water level rising when the water is 6 feet deep? It's a very good question. So what I'm going to do is I'm going to draw a picture. I have a conical tank. So it's a cone. And I don't know how they get it to do it, but it stands like this. Probably some sort of bracing on both sides, obviously. And we know that the height of this tank is 10 feet. And we know the radius of this tank is 5 feet. And we have some water being filled up in here. And somewhere in here is where the water level is at, and we're going to call this level H. We're going to call this level R, or sorry, not level. We're going to call that radius R, because we don't know what that radius is right now. All right, so this is filled with water, and we want to know what is the rate of, how fast is it being filled up. So we're looking at the rate of the volume. So we need dV dt. Oops, I'm sorry. I misread the problem. We are looking for how fast the water level is rising, not how fast the volume is rising. Sorry, my fault. Not paying attention as I'm writing here. We're looking for the derivative of h with respect to t. We're looking at how fast the height changes, the water level, right? And there are things that we know. We know dV dt, because I wasn't paying attention. dV dt is 9, because it's going up at 9 cubic feet per minute. Now, here is a thing. We're going to get to this. Let me just write some stuff down first, and then I'll get to that. All right, so you might remember the volume formula. Since we're looking at volume of a cone, volume is 1/3 pi r squared h. Now, here's a problem that we come across with this particular example. There are 3 variables, but we only know dV dt, and we need dH dt, which means I have no idea what r is right now. So there is a way that we can eliminate the r value. Now, if you think about the fact that we have two right triangles in here, and they're similar right triangles because they share an angle and share the size, that sort of stuff. So I can actually do a little bit simple of ratios. I know the ratio of R to H is the same as the ratio of 5 to 10. So no, R to H is 5 to 10, which means I can say that H is equal to, this is half, right? H over 2. Well, that's super, super nice because now I can change this formula to V equals 1/3 pi times H over 2 squared times H. And if you simplify this down, this becomes 1 over, actually let's call it pi over. This becomes 4 times 3 is 12 H cubed. Now you notice that our formula now only has H's and V's, which is super nice because, one, it makes our problem simpler, but it also just compares the two things that we need and we know. All right, so if we take the derivative of V with respect to t is equal to the derivative of this thing. Bring the 3 down, I get pi fourths H squared times dH dt. I know dV dt, and I actually do know H because it tells you that you want to know something about when H is 6 feet. So that means I know this. So I know everything now that I need. I know that dV dt is 9. I know pi fourths is pi fourths. I know H is 6 squared. And then notice now everything is just numbers. And I can just go straight to it. I can go, okay, 9 equals. 6 squared is actually 36. And the 4 cancels with the 36 to get 9, which means now I have 9 pi dH dt. And if I divide both sides by 9 pi, I get 1 over pi equals dH, oops, not dH, that's silly, dH dt. And if you did this on the calculator, that is approximately 0.32 feet, actually cubic feet. Wow, 2 became a T. It's one of those, I say words and then I don't write them. 0.32 cubic feet, not cubic feet, man alive. Oh, feet per second, because this is the rate of change to the height. Feet per minute. There we go. Okay. Doing the math okay, and then I get all these weird little things right now. All right, so that's our 3 examples for the day. I feel that this is going to be a little bit like 4.4, so we'll take a couple days. We'll adjust as we need during class time. I know this section and section 4.4 are hard, but like I mentioned at the very beginning, these are some of the best types of problems that calculus and derivatives have to offer. After we get out of this chapter, we're going to really get into anti-differentiation and integrals and all that sort of fun stuff. Then we can really start jumping deep into our AP practicing. I'll get you guys some stuff, obviously, for Christmas break, that sort of fun stuff. All right, so I will see you guys Monday. Start this stuff tonight if you get a chance, just so you can get a feel for these problems. Maybe after the section 4.4, this is actually going to be kind of easy. Who knows? All right, so have a good time with this. See you guys tomorrow.